Welcome back to Kubernetes with Typical Monk. Class 2, from containers to orchestration. Last class, we saw why Kubernetes exists, to run our containers for us automatically. But before we can master the orchestra, we must truly know the instrument it conducts, the container. So today is a careful recap, rebuilding the container from the ground up. We will see what a container actually is underneath, not magic, just a clever use of the Linux kernel. We will nail the difference between an image and a container, because that exact distinction reappears as the pod in Kubernetes. We will meet the container runtime interface and clear up the common confusion about Docker's role inside modern clusters. And then we will feel, concretely, the limit of a single container host, the precise gap that Kubernetes was built to fill. By the end, the leap from I can run a container to I need Kubernetes will feel not like a jump, but like the obvious next step. And that is really the goal of every recap, not new facts for their own sake, but making the ground so firm underfoot that the harder ideas ahead have something solid to stand on. In Hindi and English together, one idea at a time. Here is today's map, 6 ideas that carry you from the single container to the need for a cluster. First, what a container actually is, rebuilt from zero. Second, images versus containers, blueprint versus running instance. Third, registries and image tags. Fourth, the container runtime interface and Docker's real role today. Fifth, the hard limit of a single host. And sixth, the bridge from a container to a Kubernetes pod, one idea at a time. Let us rebuild the container from zero, because half the mystery of Kubernetes dissolves once you truly understand this. At its heart, a container is not a tiny virtual machine. It is just an ordinary process, a normal running program, like any other on your computer. There is no separate operating system inside it. That is the secret to why it is so light and fast. This is the crucial difference from a virtual machine. A VMX carries a whole guest operating system, gigabytes heavy and slow to boot, while a container shares the host's kernel and starts in a fraction of a second, which is exactly why you can pack dozens onto one machine. What makes that plain process a container is 2 features of the Linux kernel. Namespaces control what the process can see, its own view of the file system, the network, the process list, so it feels alone on the machine, even though it is not. And groups control what it can use, how much CPU and memory it is allowed, so it cannot starve its neighbors. Together, these 2 kernel features are the whole trick. There is no magic and no separate machine, just an ordinary process that the kernel has been told to fence off and ration, an understanding that quietly demystifies the entire container world. Wrap that isolated process together with its own file system layer. Everything it needs to run, bundled in, and you have a container. See only, your own, use only, your share, carry your own dependencies. So the takeaway, a container is simply an isolated package process. Namespaces decide what it sees, groups decide what it uses, and that lightness is exactly why we can run so many of them. Remember this the next time someone calls containers lightweight VMS. They are not. They are something simpler and cheaper. And that cheapness is the very thing that makes orchestrating hundreds of them practical. Now, the single distinction that people blur most often, and the one that carries straight into Kubernetes. The difference between an image and a container. An image is a read-only blueprint. It is a frozen, packaged snapshot of your application and everything it needs, built once on your machine or in a pipeline and never changed after. Think of it as the recipe, written down. A container is a running instance of that image. You take the read-only blueprint and bring it to life, and you can start many identical containers from the very same image, just as one recipe can cook many identical meals. This is why containers deliver on the old dream of "it works on my machine" being true everywhere, because every instance comes from the identical frozen image. The one that ran on your laptop is byte for byte the one that runs in production. Hold this pairing firmly, because it reappears at the very heart of Kubernetes. The image is still the image, and the running unit simply gets a new name. the pod. Learn it here, and half of Kubernetes will already feel familiar. Beginners who blur these two words struggle for weeks. Those who keep them crisp find that pods, deployments, and the rest slot neatly into place, because it is all just images being turned into running instances managed for you. So the takeaway: an image is the read-only recipe. A container is the running meal made from it. And that same idea becomes image to pod in the Kubernetes world. So you have built an image on your machine. How does it get to the servers that will run it? Through a container registry. A registry is simply a storage service for images, Docker Hub, or a cloud one like Amazon EK. It is the shared shelf that every machine can reach, the middleman between where an image is built and where it runs. From your build machine, you push the finished image up to the registry, uploading it once, so it lives in a central, trusted place. And then any machine that needs it, every node in your cluster, pulls it back down to run. One crucial discipline makes this reliable: use immutable tags, meaning a given tag, once published, always points to the exact same image forever. So what you tested is precisely what runs in production. The opposite, reusing a moving tag like latest, is a classic source of 3 in the morning mysteries, where the same tag quietly points at different images on different days, and no one can reproduce the bug. So the takeaway: you push an image to a registry once and pull it anywhere it is needed. And immutable tags are what keep your deployments reproducible and trustworthy. Now let us clear up something that confuses almost everyone new to Kubernetes: how it actually runs containers and where Docker fits. Kubernetes does not run containers itself. On each node, the kubelet, the agent from last class, delegates the job to a standard called the Container Runtime Interface, the CRI. Through that interface, the kubelet talks to a CRI-compliant runtime, commonly containered or CRI-O, which in turn drives the low-level runtime, Runk, the tool that actually creates the container from the image, following the OpenOSI standard. This layering is not bureaucracy. It is what lets Kubernetes stay independent of any one vendor. Because it only speaks the standard CRI, you can swap the runtime underneath without the cluster ever noticing. A clean chain of responsibility, each layer doing one job. And here is the surprise: Docker Engine itself is no longer in that chain inside a cluster. Since Kubernetes version 1.24, the old bridge to it, called Dockershim, was removed. Docker is still a wonderful tool. You still use it to build images, but it is no longer what runs them inside Kubernetes. When this change first landed, headlines screamed that Kubernetes had deprecated Docker, and a wave of panic followed, almost all of it based on a misunderstanding of this one narrow internal detail. So the takeaway: kubelet talks through the CRI to containered or CRI-O, which uses Runk to run the container, and Docker's job in this world has narrowed to simply building the images. That last point trips up so many people that it deserves its own moment, because the headline "Kubernetes dropped Docker" was widely misunderstood. Let us set it straight. Docker is very much still used and still essential. You use Docker build to create your images, and Docker is a superb tool for local development, for running and testing containers on your own machine. Nothing about that changed. What changed is only one narrow thing: Docker Engine is no longer used to run containers inside the cluster itself. That role passed to the lighter CLI runtimes, and the Dockershim bridge was removed in version 1.24. And crucially, this is the part that reassures everyone: the images that Docker builds still run perfectly on Kubernetes. Image formats are standardized by the OSI, so a Docker-built image runs identically under containerd. Nothing you built is wasted. So the practical upshot for you is wonderfully boring. Keep using Docker exactly as you always have to build and test, and Kubernetes will happily run the results. The change is real, but it barely touches your daily workflow. So the takeaway: Docker still builds the images, and the cluster simply runs them with a lighter runtime. Kubernetes dropped Docker only ever meant inside the cluster, never on your desk. Now let us feel concretely why a single container host is not enough. Because this is the exact pain Kubernetes removes. Picture one Docker host, a single machine, happily running 3 containers. Everything works, the app is up. For a hobby project, this might even be fine. But then one container crashes at 3 in the morning. On a single host, nothing is watching. Nobody notices, nobody restarts it, and your service is quietly broken until a human wakes up and looks. And it gets worse if the whole host itself dies. A hardware fault, a power cut. Then all 3 containers vanish at once, and your entire application is simply gone, with no fallback anywhere. This is the quiet terror of running anything important on a single machine. It is not a question of whether it will eventually fail, but when, and on that day, with a single host, you have no answer ready. So the takeaway, a single host has no safety net, no one to restart a crashed container, and nowhere to go when the machine itself fails. And that fragility is unacceptable for anything real. Now watch how a cluster solves exactly that problem. This is the precise gap Kubernetes was built to fill. Instead of one host, we have several machines joined into a cluster, call them nodes, and our containers are spread across them, rather than piled onto one. Already we are safer, because no single machine holds everything. Now, when a container dies, the story is completely different. Kubernetes is always watching, comparing what is running against what you asked for. Within seconds, it notices the missing container. And it does not wait for a human. It instantly starts a fresh copy on a healthy node, all on its own, in the middle of the night, with nobody paged. Lose a whole node, and it simply reschedules everything that was on it, elsewhere. That is self-healing. So the takeaway, a cluster spreads your containers and heals itself automatically, restarting what crashes and rescheduling what is lost, which is the exact capability a single host can never have, and precisely why Kubernetes exists. Finally, let us build the bridge from the world you know to the world you are entering, from the container to the pod. On one side is the container, the unit you know from Docker, the isolated, packaged process we rebuilt today. It has served us well as the foundation. On the other side is the pod, the basic unit that Kubernetes actually runs and schedules. And here is the reassuring truth. A pod is not something exotic. It simply wraps one or more containers together, adding the small amount of extra information Kubernetes needs to run them. So, you are not throwing away anything you learned about containers. You are wrapping it in one thin new layer. We will deepen the pod fully in Module P. Today, just hold the bridge. The container you already understand becomes the pod you will soon run. So the takeaway, the container is the Docker world unit, the pod is the Kubernetes world unit that wraps it. Same idea, one thin layer up, and everything you know still applies. Let us gather the whole class in one breath so it locks into memory. A container is an isolated packaged process. Namespaces control what it sees, groups what it uses. An image is a read-only blueprint. A container is a running instance of it. Registries store images. You push once and pull anywhere using immutable tags. The kubelet runs containers through the CRI. Using container or CRIO, Docker now only builds the images. A single host cannot self-heal or scale the exact gap a cluster fills. And the container you know simply becomes the pod you will run. Next class, Kubernetes architecture, deep, the control plane, and node components. One idea at a time. From one to many. Today we did something quietly important. We made sure the ground beneath Kubernetes is solid. A container, you now see clearly, is no black box. It is a lightweight, isolated process born from an image, run by a small chain of standard tools. And the reason we need Kubernetes at all became concrete, not abstract. One host has no one to restart a crash and nowhere to turn when it dies, while a cluster spreads the work and heals itself without a human in the loop. That single leap, from a lone container on one machine to many containers, self-healing across many machines, is the whole story of orchestration. Everything you learned about containers still holds. We are simply about to run them at scale. Next class, we open up the cluster itself and study its architecture in depth. One idea at a time, from one to many.